Hi everybody, Dario Fresu here from fresuelectronics.com, and today I wanted to show you how does the return current change based on the frequency, and also how can this affect the way we design our PCB layout, but most importantly, how can this have an impact on the results that we get in EMC and signal integrity. So today we're going to look at different signals and how the signal propagate in the printed circuit board. So in here we have a simulation which is made with the Symbiote, which is a software that runs electromagnetic simulations. This that you see here is a signal on the top trace, and this on the bottom is the return reference plane. So we have one signal trace in here, and we have a return reference plane underneath it. So this is just adjacent to the signal trace. So I can show you how does this look like in a PCB. So you can see that in here, in this PCB, for example, we have the top layer with the signals on the top, and then we have the plane, which is a full plane without cut, without splits. So this is a full return reference plane. So we're going to see how does the signal behave when it's running at different frequencies. So we will have different signals in here. One is going to be 1 gigahertz and the other one is going to be 10 kilohertz. And we are going to see how the return currents will behave in these circumstances. So when we have low frequency signals, then the return path is going to take the path of least resistance. So this means that this term, which is the reactive part, is going to be small, and the impedance is going to be more resistive than reactive. So this means that then the signal will try to find the path of least resistance, the shortest path back to the source. Then when we have high frequency signals, this part in here becomes larger because it's dependent on the frequency, and then the return current will try to flow back as close as possible to the signal trace. So this means that in this case, if we have a low speed signal that is flowing in this trace, then the path of least impedance is going to be the shortest path to the source. So when we're talking about the shortest path, we're talking about the shortest path that the current takes to close the loop and flow back to the source. This is important because we have to remember that the current always flows in loops. So you can see in here the loop is created from the signal trace in here and from the return path. So there is this loop in here that the current takes to flow back to the source. Instead in here, we still have the loop, but this time the loop is much closer to the signal trace because the signal does this way and then flows back to the source, because this path in here is the path of least reactance, which is really inductance. So we'll take the path of least inductance, and we're really going to see it in here with the simulation there. So we have in here 1 gigahertz signal, and we see how the return current flows back to the source. So we can see that this is when we have 1 gigahertz signal, the return current, which is this one that you see in the arrows here, will stay as close as possible to the signal trace. So it stays very close to the signal trace. It doesn't go this way, like this, but it goes this way. But then now we're going to see how does it changes when we have a 10 kilohertz signal. So let's put now a 10 kilohertz signal. You can see here. And you can see that now the current will start to spread much more in the plane in here. So it's not yet at this point because we still have 10 kilohertz. However, right now it's trying to take also this path. This is 1 gigahertz and this is 10 kilohertz. So you can see how much more it spreads through the return plane. So you can see this is the same as the simulation. You can see that if we have a 1 gigahertz signal, the return current will flow back under the trace in this return reference plane, in this big return reference plane. But when we have 10 kilohertz signal, then the current will start to spread much more. So this is very important for us because what we can do with this information, we know that when we're doing the layout, if we have a high speed signal, the return reference plane, which is right now in the second layer, it has to be as close as possible to the top layer in here where the signal trace is laid out. But also it's important because it means that we have to be careful about what we put next. So if we place in here another signal too close, supposing this way, now what happens when we place in here another signal next to it, and the signal now is low frequency signal. But then the return signal of this trace in here will try to cut corners to flow back to the source. And what happens is that then this signal in here will also see this return current under its return plane. And this is what we call the ground bounce. So the ground bounce is basically a crosstalk phenomenon. And this is what causes the signal integrity issues in our electronic circuit. But now the next point in here that I wanted to show you is what happens when the trace is longer. So we still are 1 gigahertz, but you can see that the signal is still flowing under the trace. And what happens when we use 10 kilohertz is that now the only part of the plane left is this part in here that has no current flowing through it. But you can see that here still has some current flowing through it. Now, the same will occur when we change the signal trace. When we have a signal with 1 gigahertz signal, you can see that the signal is flowing back to the source under the trace. It's not taking the shortest path in here of listed resistance. So what happens when we introduce a cut in here in the green return reference plane? This is exactly what's in here. So we still have the signal trace, which goes all around this plane in there. But this time we cut the return reference plane. And this is what we see in many designs, that sometimes we have a signal layer on the top and then the bottom plane has some cuts. So it's not full like in this case, but it has some cuts in the plane. But now the problem is what happens when we cross this split of the planes with a signal trace. And this is exactly what this simulation is going to show you. Because you can see we can run again 10 kilohertz signal. And what is the problem in here? This is the signal trace, which goes all around. Signal reaches here. But now what happens is that the return current will now go around this cut and then will flow back to the source, doing all this big, huge loop. So now the problem is with this big, huge loop in here, because this big loop that we have is what is going to create some issues with the other signals, because the return current, not the signal forward current, but the return current now will cause some problems in the signal routed on top in here. Because still the signal routed on top in here will see this return current, and this will result in bad signal integrity for our electronic circuit. Now the worst happens when we have signals which can cause some resonance in this cavity. So this is again 10 kilohertz, and then we can go back in here to 1 gigahertz. Now you can see that the return path of the signal is under the trace. It comes in here, returns back, try to flow back to the source, but then when it's trying to flow back to the source, you see this cut in here, and then it takes this path, but then at this point in here, it resonates back and forth. So this means there is energy in there which starts to resonate, and then it goes back to the source. And this is what is going to cause not only issues in terms of signal integrity, but also in terms of electromagnetic compatibility, because at this point we have uncontained energy in here. And this is basically what becomes an antenna for our design. And then here we have also the case where we have the return path, which is at a larger distance from the signal trace. Still, it does not return back like in this case, because the frequency right now is still too high for the signal. So this point in here will happen when we have frequency very close to DC level. So when we have frequency close to DC level, then this is what is going to happen. But if we have this part of the impedance which is still high, because still we have some frequency here that are not so close to the DC level, then the current will not take this path to return back to the source. And then you can see in here also with a split in the plane, what happens when we have this frequency in the signal. So we would expect the signal to flow back and do this. But what really happens is that when we have the cut, so it doesn't go anymore in this direction like before, but this time it goes back through this cut and then it flows back to the source. So really having a return path with an impedance discontinuity, because this is what it is. This is an impedance discontinuity So the impedance of the return path in here has a discontinuity. So the signal needs to find better ways to flow back to the source and spend the least amount of energy possible. So it will not go back in this direction when we have the cut in the plane, like in this case, but it will actually go around the cut and then flow back to the source. And this can create a signal integrity issues because we don't have only one signal, but usually we have multiple signals running. So imagine what happens if I introduce the cut in here. Then the signal in here to flow back to the source has to do all the way here. And also these signals, all these signals in between, we'll see that there is a signal going under them. And this is going to cause signal integrity, but also EMC issues. So I hope that right now it's clear for you what happens when we introduce, first of all, cut in the return or reference plane. We don't do that. We don't break this beautiful plane in here. We don't break it. We don't make a cut. We don't make splits. So each time that we choose a stack up, we try to make sure that the signals, they have a good return reference plane underneath, because otherwise their return current will be compromised. And then this is going to cause signal integrity issues, but also EMC issues, like we just show in this case where we created, in this point in here, we just created an antenna. You can see this is a nice antenna that we just created for ourselves. So we don't want to do that. And I hope that you find this video helpful. And I see you either in the next video or I will see you in the new PCB Hackers Academy that we just saw. Bye bye.